Well, I'm delighted to be here. I think it's my first visit to the IAP, but I see friends that I have known for many years, and especially Roya, who I've worked with now for a long time trying to make the James Webb Telescope happen. So there are many stories to tell, and I guess the basic one is all of these projects are huge team efforts. When a Nobel Prize comes to a NASA mission, it's because there were 1,500 people that worked on it together, and so we learned how to do big projects, and now we're trying even bigger projects. So now I guess I'd like to tell you how we're doing on the James Webb Telescope. I want to summarize the scientific objectives that people have, something of the design, and show you some of the progress. I know we're much in the news lately. I don't have an end to the story to tell you, but people assure me that this is all going to work out, and we're going to be able to finish the telescope as we have planned. So we'll give it a try anyway. What I hope to show you is that the technical part, the engineering part, and the scientific part are in good shape. So when we started the project, we outlined 4 major areas of science, which we thought people would be interested in using the observatory for, ranging from the first objects that formed after the beginning of the universe to the assembly of galaxies from small parts. Now, 15 years ago when we started the project, we didn't have the degree of supercomputer simulations that we have now. We hadn't seen as far as we have with the Hubble, so it was even more mysterious in those days. We knew that we'd like people to study the formation of star systems and planetary systems. This was 15 years ago. We had just found the first few planets around other stars. Now we have the hope of actually learning a tremendous amount about other planetary systems, especially through transit spectroscopy, which can be done very well with this observatory. So here is a summary of the, actually it's hard to see up there. It's a summary of the observatory characteristics. As you know, it's an international partnership of the United States with European and Canadian space agencies, and also not named here is the fact that one of the instruments is being produced by a European consortium, which has, I think, 14 member institutes around Europe. So it's a huge project. Northrop Grumman is our prime contractor. They build a lot of the American aerospace systems, not just for astronomers, but for other government agencies, as we like to say. They're very enthusiastic about this project because they have a related interest in observing the Earth from above. So our instruments include 4. There's a near-infrared camera, a near-infrared spectrograph, mid-infrared instrument, which is this should say JPL, European Space Agency, and the European Consortium. And finally, there's a fine guidance sensor that comes with a tunable filter imager from Canada. Now that one we're changing at the moment because they've had some trouble with that, but we haven't got a new chart yet to show you. And the operations will be done as the Hubble operations are done through the Space Telescope Science Institute in Baltimore. So when it's time for you to write a proposal, you'll do it just the same way that you do it for Hubble. We have already started putting in the little connections in the proposal tools so you can see how to do this. And there's already an exposure time calculator available for the instruments, even though they haven't been attached to the telescope yet. We know how well they're going to work. So let's see, it's a telescope with a 6.5 meter diameter. I'll show you that we're doing quite well on that part. It's cold. This telescope runs about 45 Kelvin. And the instruments behind it are even a little colder than that. So Europe is providing the rocket vehicle, the Ariane 5. We have been pleased to see a long string of successful launches from the Ariane. So we like that. However, there was a certain NASA administrator who didn't like us to accept this proposed rocket. So we spent a couple of years waiting until we got a new NASA administrator so we could accept the European contribution of the Ariane 5. We are planning for a 10-year mission. We can only insist on, the engineers can only insist on a 5-year mission, but we're carrying fuel enough for 10 years of observations. So this is what it looks like in, well, none of these are photographs, of course. The engineering design shows this 5-layer umbrella, a sun shield here to protect the telescope, the sun and the Earth are over here. Telescope is here. It's always in the shade. Sun never hits the telescope. So we fly around the Sun-Earth Lagrange point, like the Planck and the Herschel and the WMAP, so that we have this one-sided sunshield works quite well. We don't have interference from them. You can see here that it's an extremely interesting problem to fold it up to go inside the rocket. This is about as big a rocket as we can get. If you want a telescope this large, this is what we have to do. Someday, when the United States actually builds their larger rocket, we may be, as astronomers, have greater ambitions to have a telescope that does not have to be folded up, or that can be even larger, maybe a 10 or 12, 20, or, well, however many meters you can afford. So this is a drawing of the mirror size. There's the Hubble, the Spitzer, and the new one, the James Webb, and you can see that it's truly immense. The spectral range of the JWST overlaps both Spitzer and Hubble. But I don't think we touch what the Herschel can do. We don't overlap exactly. So where we can look? We can look anywhere in this range of angles away from the sun. We can look 5 degrees closer than the ecliptic pole, and we can look 45 degrees further away. So about 1/3 of the sky is available to us any particular day. And so if you wait 6 months, the entire sky is visible. So key features of the design. Here are many images from the computer of how this telescope could look. Here's the sunshield, the deployed telescope. From the other end, you can see there's a solar array, which has also got to be deployed after launch. Here is a thing you can barely see. This thing is called a momentum trim tab. Here, that's there to sort of balance the solar radiation pressure. The total solar radiation force on the sunshield is about 1 millinewton, and if that were not properly balanced, there would be a torque, which would tilt over the telescope and would eventually be a problem. So before launch, we calculate all of this, and we set this trim tab so it helps us steer better. So here's a drawing, a computer drawing of the deployment of the observatory. After launch, it's done within a few days of launch. Some parts, like putting out the sunshield, so the solar array, happen right away. Here we're unfolding the sunshield. The one in real life will be about 10,000 times slower. So then we raise the telescope up on a tower to get it away from the warm part of the observatory. Now the covers are coming off the sunshield, and then we'll see the sunshield will be deployed. This is completely amazing engineering to me. And if you're a mechanical engineer, you should be either very thrilled or very worried. Because this is, of course, the first time that we needed a sunshield the size of a tennis court in outer space. So we have been practicing a lot with the small models, larger models, deployment tests, and everything that you could imagine that you would need. There will be many tests of that deployment. Final step is to unfold the telescope and eventually focus the observatory on distant stars. So this is probably one of the more complicated things that one could imagine. The company, by the way, the Northrop Grumman, says this is not the most complicated thing they've ever put out into outer space. It's in the top 5. So you can only imagine what those other things are. So the optical design, the telescope is a improved Cassegrain telescope. It's called a 3-mirror anastigmat. So this is an almost parabolic primary, a hyperbolic secondary. There's an ellipsoidal tertiary mirror. Over here, where you can't quite see it, is a folding mirror that can move very quickly. And finally, the focal surface, which is shared by the instruments. So focal length of 131 meters. A collecting area of 25 square meters. So this is a tabulation of the instruments that go in. You know, near-infrared camera in 2 bands simultaneously and has a coronagraph. That's also the equipment that is used for recognizing when the observatory is focused correctly or not. So the wavefront sensing equipment is in there. The near-infrared spectrograph is a European project with Astrium as the prime contractor. It provides spectroscopy over this whole wavelength range with one kind of detector. And it has not only a micro-shutter array to choose targets, but also an integral field unit and some fixed slits. The mid-infrared instrument is the one that comes from the consortium in Europe, and it's led by the UK Advanced Technology Centre. Gillian Wright doing that part, and that has spectroscopy and imaging and a coronagraph. Finally, the fine guidance sensor and the tunable filter imager come from Canada. So they share the field of view. In principle, all of them could be operating simultaneously. In practice, it's unlikely that we'll be able to do so because they all need shared resources. But at any rate, that's how they're laid out in the focal plane. Oh, come on. So this is a summary of the capabilities of the observatory. The imaging is extremely good. I'll show you a simulated point spread function. So although it's defined as diffraction limited at 2 microns wavelength, it's actually quite good at shorter wavelengths as well. The sensitivity of the cameras is limited by the photon noise of the cosmic background, of the zodiacal light and the starlight out there. The spectrometers are limited by the detector noise, but they're extremely good detectors. They will be even better. Anyway, we'll get to that. So it's very good. There are a few things that I love to show because they are enchanting. This is a simulation of the formation of galaxies. And of course, we cannot see this happen with any kind of equipment. Only the computer people can see this. But our challenge as astronomers is to figure out if any of these computer simulations are correct. There are wonderful details and complexities in there which we can barely recognize when we see them in the sky. But by pushing the limits of time farther back towards the earliest objects, we certainly hope to learn more about whether these computer simulations are correct and where they diverge from reality. Another thing that I love to show people is that by about the time that the sun burns out, the Andromeda Nebula is coming toward us, and I'm afraid we won't be here to see this, but I think it would be the best we can do is to look at other galaxies in the process and imagine what it would be like when this occurs for us. So top targets, as people identified before, we want to see what happened in the early universe. When you look at the deepest picture we can get with the Hubble Space Telescope, what you see are little tiny things. The tiniest things on here, the reddest things, are the ones that are tempting. They're just barely at the limits of what we can find. And I think I look at this beautiful picture and I say the thing we want to know is not on this picture. There will be some even fainter, even redder objects which the James Webb Telescope can see and nobody else can see. So I don't know what they look like. But that's one of the enchantments of this kind of project. We certainly are going to be looking for the first stars. Now, we cannot see them individually until they explode. But there are quite a number of different kinds of supernovae. And so this one here, I'm not quite sure what the current interpretation is, but it was a lot brighter and lasted a lot longer than the typical ones that we think about. So they're pretty easy to see if we know where to look, but they're also pretty rare. So we're probably going to be using observations from other observatories that cover the sky much more thoroughly, like the Large Synoptic Survey Telescope, to say there's something that happened over here, please look here. Our field of view is about the same as Hubble, so we cannot survey the whole sky. Another thing that's interesting and different is if you're looking at a redshift of 9, then one of these things takes 10 times as long to do its process, so you have to be very patient. What was a few days is now a few weeks or a month, and so we will be returning to the same fields of view on the sky many times over the course of the mission to look for changes. The search for the end of the dark ages is one of the things that's of great interest and has been for many, many years. We expect to be able to see the objects that reionize the universe. And so maybe we'll know what they are before we get there, maybe we won't. But a very large collection of them will be available to much higher redshift. We certainly are going to be interested in using the telescope for studying the dark energy. The dark energy is a pretty tricky subject, but because we can see farther, we can do a lot more things about the supernova light curves, and there are possibilities of improving the distance ladder greatly by using the infrared observations that we can do. So star formation is great interest, and when I was a graduate student, everyone knew that star formation was going to be understood sometime soon, and I think it's still not understood. So what James Webb Telescope offers is the possibility of seeing inside the dust clouds where the picture is much clearer, and we have a hope of seeing much closer into the first generations of stars and the conditions that are occurring inside the dark nebulae. So another thing that happens when you use infrared, basically the infrared light is long enough to go around the dust grains, and so you can see inside a cloud like that to see a young star producing jets coming out. So these are both Hubble pictures, and so this is the longest wavelength that Hubble can see. There's the visible picture, it's completely different. So we certainly anticipate a similar change of what we can see with the JWST. So planets are going to be of interest as well for us. We have two strongest methods that we think people will use. One is to look at the direct imaging, as Hubble has done. Another is to study the transits that occur so that we can get the chemistry of planetary atmospheres. So there is already a catalog of 1,235 new candidates from the Kepler mission, and they would all be good candidates for following up with JWST. Something that's a lovely surprise that happened quite recently, we now know that there are at least 10 planets that have no stars associated with them. These were found by the microlensing technique just a couple of months ago, I think. So anyway, many things we expect to do. Oh, this is movies about the transiting planets. One thing that I hadn't expected is when you think about it enough, there's even the possibility of recognizing moons around planets. Because of the way that they would affect the timing of the transits, or even possibly if they're very large moons, might be individually detectable. So both of these, both the transit technique and the secondary eclipse, where the planet goes behind the star, both have already been measured, and much more will be possible with JWST. So people have also taken a great interest in the outer solar system. Let me skip this one. In the outer solar system, there are lots of candidates out there, and we imagine that JWST will find hundreds and thousands more. So where are they? There's a whole host of them out there. Mostly, many of them are in resonant orbits with the outer planets. So now I want to talk about the progress we're making on the hardware. As you know, it's a huge project, and so this illustrates the parts that we're currently working on. Many, many pieces have to go together eventually to make the telescope. Rather than dwell on this, just show you some of the key things that we're doing. The primary mirror is made of beryllium, which is an unusual material to use except for cryogenic telescopes. And we chose beryllium because it can keep its shape when it's at low temperature. This illustrates that we start with a block of solid beryllium. We cut it, and we cut pockets in the back so it's extremely lightweight. Eventually, you would be able to lift one of the mirror segments. It's extremely lightweight. Eventually, it gets coated with gold as well. So there's a whole process to go through to prepare these, and I'll show you a little bit about them. Here is a picture taken in our test chamber down at the Marshall Space Flight Center. By the way, if you worked on X-ray observing, this used to be the X-ray calibration facility for Chandra, for instance. Now it's been converted to a cryogenic facility as well, so we've been testing mirrors in it for many years. So here we have 6 of them in the chamber at one time, all to be tested. So this is a drawing that shows that we have measured the shape of all of the primary mirror segments, and they are all extremely good. The RMS error is typically 10 or 15 nanometers. The average comes out to be 13 nanometers. So if you had a telescope and you had one optical element in the telescope, this would be a UV telescope. Because our telescope has got many parts and they all have to be adjusted to match each other, it's not quite that good, but it's a very amazing technical accomplishment. So all of them have been measured and polished to the right shape. We've done polishing the mirrors. So 14 of them are also coated with gold. So they're just individual pictures of them. The secondary mirror is trickier to polish than the others because it's convex, but it's come out to be extraordinarily good. The measured surface error is in a few nanometers range. So in principle, if you wanted to make a ultraviolet telescope in the future, this technology would be sufficient. It's probably not your best choice because this one is optimized for low temperature, but for the future people with great ambition who want to build the next ultraviolet telescope, it's going to be possible. You can have a wonderful one. So here is I guess you can't hear my little loudspeakers. Here is a test of one of our primary mirror segments. We vibrate it and try to see if it will change. And the answer is no, they do not change. They survive their vibration test very nicely. This other figure shows a movie of installing one of the hexagonal segments in its fixture. This is a little bit scary, but it's work, so we have to do this. So other parts in the telescope, there's a big beryllium frame that holds additional mirrors. I'll just show you that they're also coming along well. This is the third mirror in the system, the tertiary mirror, and it's come out also very good. There's a little fine steering mirror. Now the Hubble telescope steers like a solid object. It's entirely rigid. This telescope cannot be steered as a solid object. It's too flexible. And so what we have to make it capable of tracking more quickly is that there's a small mirror at the focus. It's an image of the pupil. And this tiny mirror, which is only this big, can be steered very quickly to stabilize the image. It's hard to get it to stop there. Anyway, this curve, our set of curves, shows that the gold reflective coatings are all very good. The specification was here, and the reflectance of each mirror has been measured, and at least in the long wavelengths, it's over 98%, as we required. This is a drawing or a simulation of the predicted image quality. The requirement is diffraction limited at 2 microns, and the near-infrared camera produces Nyquist sampling. So this is about what we should get. One very bright central peak and a somewhat imperfect image that you can recognize, but anyway, it's very good. At 1 micron, we don't have Nyquist sampling, but you can see that the image actually is even a little bit sharper. So people will be very happy to use this even at the shortest wavelengths that we can study. So some pictures of the instruments as they're coming along. Engineering drawing here of the near-infrared camera. And here's the optical sketch. Light comes in from the telescope, and it's actually divided into 2 different channels by a dichroic filter right there. The long wavelengths come here, and the short wavelengths come here. Each of these has 2 wheels in the pupil, and so there are filters and polarizers and wavefront sensing equipment in those wheels. Here is a picture of the engineering test unit, and we learned a few things about the test unit that we did not like, so we have had to make some changes in the flight unit, but that's what the test unit is for. Here is a sketch of the optics for the spectrometer. This is the European spectrometer. It's being actually built by Astrium near Munich. And so this is the sketch. Light comes from the sky, is focused onto a micro shutter array, and we have 250,000 shutters that can be opened or closed by command from the ground. We let through the light from the selected galaxies, and it goes through the imaging spectrometer, comes out on the detector. Here is another engineering drawing, and then I'll show you the real thing. This is all made of silicon carbide, by the way. You would not necessarily think silicon carbide was a wonderful material for the space business, but it's pretty lightweight, it's very strong and stiff, and you can make mirrors and optical bench out of the same thing, which is good. So we can open up any desired pattern of the shutters, as this suggests. So here is the real one. This is the flight near-infrared spectrograph. It will have covers eventually, but this is what it looks like without the covers. And so it's being tested, and we're pretty pleased with it. It's more efficient than was expected to be, and so the sensitivity will be quite good. So here is the micro shutter box as installed. The micro shutters are a tremendous technical accomplishment, which was carried out by my colleague at Goddard Space Flight Center, Harvey Moseley. Many of you may know him. Here are pictures of the micro shutters, and they're extremely tiny, but every one is controllable by command from the ground using magnetic and electric fields in combination to move the shutters. So this is a first light image from the near-infrared spectrograph, and you can see multiple things here. These are the images that come from the pseudo slits of the imaging of the integral field spectrometer, the image slicer part. These are the spectra that come from the fixed slits, and there are a few of the micro shutters that were open when they weren't supposed to be, so that each of them gives a little rainbow over here too. So this is as expected, and we're quite pleased with the optical performance. It was a very challenging optical system to design and build. It has, I think, 15 reflections. You wouldn't ordinarily think that was a good thing, but you can do it in the infrared because the reflectance of the surfaces is quite good. So the mid-infrared instrument, here's another engineering drawing. This part has been the responsibility of the European Consortium, as led by Gillian Wright at the UK ATC. So all of this is now in existence as well. There is the flight instrument being prepared for test. This one's made of aluminum, and so these 6 legs are used to account for differential thermal contraction. With all of the different sources that we have around the world for equipment, there's no possibility of having everything made of aluminum, which would have been the systems engineer's preference. But anyway, so this one's aluminum, then we have to deal with changes of contraction. So this is the one, however, that unlike the others requires active cooling to 7 Kelvin. The detectors do not work well at temperatures above that, so we have an active refrigerator with compressed helium gas going through. It's being compressed over in the spacecraft bus, and it goes through piping all the way down to the low temperature end, where when it expands, it can reach the 7 Kelvin level that we require. So this also works. This is a new technology. We didn't have it when we started the project, but now we do. The fine guidance system, this is basically the one where you lock onto a star and track it for a while. And so this one is also doing quite well. The fine guidance part is relatively elementary. The tunable filter imager has run into some trouble, and so there's a modification that's been proposed to accomplish much of the science, but without the tunable etalon. So this part, anyway, is also a flight unit, and it's going to be delivered to Goddard within the year, I think. So we've already got some of the equipment in at Goddard Space Flight Center. This is the big clean room. If you've been to visit Goddard, you may have seen through the big glass window where we were preparing to service the Hubble telescope. And astronauts used to come into here to practice putting the Hubble instruments into the model of the Hubble. Now what we've done is taken all of that equipment away, and now we've brought in the test instruments for as well as a structure here that we put the instruments in to test them when they're cold. So we're getting quite far along with the test program for the instruments. Among other things, we had to build a carbon fiber structure that's about as large as an office and to demonstrate that it would keep its shape when it cooled down. So what you see, you cannot quite see the carbon fiber because it's dark, but you see all these little white objects all over it. Those are targets for cameras. We do photogrammetry to measure the change of shape as it shrinks. And so it stays its shape within a few microns of what is required. So we're very happy about that also. So the instrument package will be tested in the Goddard cryogenic test chamber. This is, by the way, the same one that was used to test the Cosmic Background Explorer instrumentation before the COBE went up. And so it's a very old but functional chamber, and it's big enough for our job here. So there will be, the instrument package will be here, up here actually, and there's a telescope simulator that simulates the beam of the real telescope, so we can verify that all of the instruments function as they do. Then they become the test equipment for the real telescope. Now I have a little movie showing you what it takes to get the James Webb Telescope into the test chamber at Johnson Space Flight Center. So it came off an airplane on a truck, and it was taken into into the big clean area. I left out most of those parts of the movie, but here is the telescope folded up for shipment, and now it's being moved, and it will be deployed outside the giant clean room, the giant test chamber, and then taken inside and tested. So here we now attach it to the handling fixture. Here we're raising the telescope. Now you'll see the telescope unfold in about the same way that it will in flight. Now we have to give it a little bit of help to compensate for the gravitational forces so we can deploy the secondary mirror tower correctly. So this is where we bring in some cranes to help with the gravitational forces. The motors are not capable of lifting the secondary mirror against the force of gravity, so we give them a little help. So there's the telescope ready to go into the test chamber. So now they have to get the test chamber ready. They're going to put in a railroad track. And here's a fixture that goes inside the test chamber. Until I saw this movie, I didn't really fully appreciate how hard it is to do this kind of test. And also, when you go up to see the test chamber from the top, it makes you dizzy just to look in. This is actually the same test chamber that the astronauts used when they were rehearsing to land on the moon for the first time. So it's on the National Historic Register. It's a national park in the United States. So you have, of course, to write some good paper to explain why you now have to change the historic artifact. Anyway, there it is. It goes into the test chamber. There will be test equipment inside the test chamber up at the top, which I'll show you in a moment. Here. So here's the telescope in the test chamber. There will be flat mirrors and optical test devices up here. So eventually we can send light through the telescope and make sure that it comes back and is in focus. This is where we demonstrate that all of our algorithms actually work to do the right thing. We've got them all demonstrated already on a scale model, but this is the real one. So it's truly immense. It's 120 feet high, almost 40 meters high. So here are pictures of people doing the tests of deploying the sunshield. This is at an early stage where we just have tables in a big clean room. So here are people. Here they are in the center of the shield, and we have people pulling on the plastic to pull it out. Eventually, of course, this all goes by motors. So if you want to know much more about the scientific possibilities of the observatory, we have recently had a conference at the Space Telescope Science Institute. If you go to their website, you can see the conference, you can see the lectures, you can get the PDFs or PowerPoint slides, and you also now can see the exposure time calculator that you would want to use to tell if your favorite object can be seen in a reasonable period of time with the telescope when it goes up. So we're very interested to have people have a look and try out the software. And I think that's just about the end of my charts. So now I think I need to tell you about the status of the observatory in terms of the federal budget in the United States. Well, as you know, the federal budget is not balanced in the United States, and people are fighting like crazy. And however, within about 10 days, they have to answer that question. They have to somehow raise the debt ceiling and get on with it. I think they will. It's hard to imagine that even this Congress of the United States would not do the right thing sometime. So, however, a little while ago, well, about a year ago, we started in on some reports telling us that we need to make some changes in the way that we were doing the project. So John Cassani, who you might know was at Jet Propulsion Lab for many years, he led two committees. One was called the Test Analysis Team, and the other one was called the ICRP, the Independent Comprehensive Review of the program. So in both cases, there were recommendations of things we should do to improve the way that we're doing the project. They said almost all of the tests that we said we needed to do are essential, so we actually will have to do those giant full-scale tests in the test chamber. They also said we don't have enough money allocated, and they were extremely critical of the way that NASA had behaved about getting the budget. So as a result, we have now got new management. All of the people who were in charge of it at NASA headquarters have been replaced, and all of the people at Goddard Space Flight Center have been replaced. So in the top management. So we think that we're actually accomplishing what the reports tell us that we should do. Nevertheless, there's a committee of the Congress which said, well, we think we won't pay any money for this. We want to teach NASA a lesson. So that's now a step in the legislative process, and one cannot really be sure of an outcome. I'm optimistic that the Congress will eventually vote to put it in the budget, because among other things, people around the world have been writing in and saying, Mr. Wolf, we really like this project. This is the hope of astronomy. All of us around the planet are going to use this telescope, so please, let's not stop now. So when we get it finished and this is all done, I think people will be extremely proud of the project, but it does mean that we have to get it right. Unlike the Hubble, we do not have a chance to repair it if it's not correct. So this is the, well, in the old days we used to make telescopes that worked the first time, but they weren't this complicated. So we certainly have taken on a very great challenge, but I think that we can do it, and I'm hopeful that the Congress will support it. So thanks for coming. I see we have a full house, and much appreciated.